Well, welcome to this next video on Interlock++, and today we're going to be looking at block signaling and how that applies to converging tracks. Now, I've covered block signaling in some other videos as if we were moving along a line of signals, but of course railway lines have points or turnouts, crossovers, all sorts of different sort of junction type things. So today we're going to be looking at these two tracks converging from two tracks into one track. Now I'm trying to keep the how-to series down to simple components. Obviously, if this line continued, it would be a diverging and a converging track at the same time. So there's another video on diverging tracks that is out as well. But today we're just going to be looking at how we deal with converging tracks. Now, the issue, of course, with converging tracks, if we look at this diagram, we have the turnout, or the point, that I've given an ID of 5. I have signal 3, signal 6, and signal 9. Now, the way block signaling works, if you like, if this signal was red, this next signal would probably be yellow, and then signal 3 would be green. The issue then is what color should signal 6 and signal 9 be? And of course that depends on the direction that turnout or point number 5 is set to. And so what I'm going to look at today is how we would deal with that situation using the interlock system. Now, the first thing to bear in mind is that this feature has been added in version 0.6 onwards. So the first thing you're going to need is to nip over to the Digital Town website and download the latest version of Interlock++. So going over to the website, all you need to do is click on the download the sketch link, and that will allow you to download the latest version. Now, within the downloaded package, there is, if you like, the vanilla version. There's just the interlock basic sketch. I've also included a couple of demonstration sketches, the one for the converging track and the one for diverging tracks, because those are the main modifications that were added for version 0.6. Going back to the top of the page, there is now the how-to section, and of course now we've got virtual signals, converging track block signals, and diverging track block signals. Click on the converging and you will get not only obviously the video that you're looking at now, but there is the download for the code for today's example. So as I've said, this is the track diagram we're going to be looking at today. Now let's take a look at the breadboard version to see what the demo system looks like. So this is my breadboard mock-up of a layout. Obviously trying to get the camera to focus on a huge layout would be a little bit complicated. So we have signals 1, 2, 3, turnout number 5. Signal 4 isn't in use for this demo. That's going to be used for the opposite direction for the diverging tracks. We've then got signals 9, 10, 11 isn't used in this, 6, 7, and again 8 is not used in this demo. Now, the way block signals work, 10 is monitoring the state of 9, 9 is currently monitoring 3, 3, 2, and 2, 1. The way the trains tend to work is going to come into this block. Signal 10 will go to red. It will then move into the next block. Signal 9 will go red, and obviously signal 10 will then free up as the train starts to leave the block. It will then go towards signal 3, and again we then see that 9 is released, and of course 10 now goes green. As the system the train continues down the track, we then go down to signal 2, and finally we get to signal 1. Now, as you can see, as the train has been moving along, if you like, our virtual train, the signals have been changing appropriately. The issue comes when we get to a point or a turnout. So it's fairly easy to monitor signals in a straight line, but what happens when the turnout changes? The way the system works is you will see obviously this signal has gone to green, this one has gone to red. But if I move this again, if you watch very carefully, hopefully the camera will pick it up, what you'll actually see is both signals go to red first, then we get the movement, then the appropriate signal is set to clear. So let's just look at that again. Now, the reason for that is you cannot move this turnout or point while you have a green signal, because if you've got a green signal, you could have a train barreling down the track and suddenly he's going to have the track change right underneath him. So part of the interlock system, before this turnout can move, obviously these signals have got to be set appropriately. Now, when the interlock system was originally devised, when I was asked to sort of write this system, the original idea that I was given was that I was going to be doing this for a signal box. Now, of course, signal boxes, from my point of view, when I think of a signal box, I tend to think of something with a man moving levers, looking out of the window and being able to see all the train movements in his area. And as such, they would physically move the signal here to danger. They'd make sure that this signal was set to danger, and then they would physically move the point and then set the signal to clear, to green or amber, depending on what the next block is. What I'm going to show you today is what I would call power box mode. Now, this is where instead of setting the individual items one at a time, one press of a button causes a sequence of events to happen. This tends to happen on sort of block signaled railways. So I was by the railway line today, and the signal that I was looking at, I think, was being operated by a panel box about 25 miles away. So he's certainly not looking out the window at the track. He's just looking at a track diagram. So what the system today we're going to look at will do is sort of simulate a power box scenario. Now, just before we move over to the code, just a quick whiz round the breadboard. I'm using the Arduino Mega. The system does run obviously on the ESP32, but I'm using the Mega just because it's got loads of pins and it's just a little bit easier to get to. I'm using two PCA 9685 boards to control the LEDs, because with the number of LEDs that I'm using for these demos, even with the number of pins that a Mega has got, I'm going to run out of pins pretty quickly. Then I've got the screen. This is the I2C backpack screen, and finally I've got my little speaker down here that gives me an alarm if I break a rule. And you'll notice in power box mode you don't hear any rules being broken. So moving over to the IDE, obviously I've got version 0.6 loaded up, and there were some mods that were made to this sketch from the previous version. There is a load signal dual monitors, which I'll do in the diverging track video. There's the list of dual monitors, and there is a change to the load signal monitors. Now, when I started on this system, because I was thinking signal box, when it came to the signals, 10 could monitor 9, 9 could monitor 3, 3 could monitor 2, 2 could monitor 1. But I couldn't envisage a system where two signals would need to monitor one signal, just because I'm thinking signal box rather than power box. However, once you get to a power box scenario, then two signals need to be able to monitor one signal. Now, what that means is that within the load signal monitors, I've had to change the function. As you load the signal, what it used to do is it would check, is this signal already being monitored by another signal? And if it did, it would throw an error and it would stop the sketch running. However, now you will get an error message number 12 in the user guide. And if you look at the user guide tab, if you now look at error message number 12, it is a warning only. So it will put a message in the serial monitor to say you've got two signals monitoring the same signal, but it will allow that to happen without causing any sort of stopping of the system. So moving down the sketch, as always, you include the interlock.h and you set up your instance of the class. There are the list of definitions. I've actually added a couple more, block clear and block occupied, because they were requested. In this example, I'm using the liquid crystal display, so I've included the wire library and liquid crystal I2C.h. And then I have got my two PCA 9685 boards. One of those has an address of 40, the other has an address of 70 because of the tabs that I soldered. And then I've also got the servo library and the servo pin. It's on pin 11 just because it was easy to do that with a single servo. Now for the blocks, I've got a number of pins being used, and as you can see, they've got their different states. And then I've also got some buttons. Now the way this is working, I've got a button on pin 10 that is connected to the button that sort of switches between training mode and full interlock mode. And then for the turnout or the point, you'll notice I've got one button for one direction, one button for the other direction. In my opinion, that is the preferred way to set up buttons to control the interlock system, because the issue is if you press a button and it's changing state, if you get an error, you've got to work out how to unchange the button state or double press it to get it back. So one button in each direction makes life a little bit simpler. I've then got my debounce. This is just for the buttons. My buzzer pin is on 12. I'm then starting the serial monitor, and then this bit of code actually prints out the file details of the sketch. I find this quite useful because it tells me which folder in the hard drive it actually took the file from, rather than just the file name. We're then initiating the system. I'm loading one input, which is a number 5, which is a point or turnout. If you want to use the other from the other side of the water, you can use turnout, and instead of point, as you can see, turnout just puts a value of 2. Point has a value of 1, makes no difference within the system. I'm then loading my signals. I've got signals 1, 2, 3, 6, 7, 9, and 10, and they are all 3 aspect signals for this demo. Right, next we're going to get down to the signal monitors, and signal 2 is monitoring signal 1. So if I just look at my diagram, 2 is monitoring 1. We then see that 3 is monitoring 2, and then we get the interesting one where signal 6 is monitoring 3, but further down the list you'll also see that 9 is monitoring 3, and then finally 7 monitors 6 and 10 monitors 9. So once I'd loaded all my signal monitors, I then needed to set up my rules. Now I tend to start with the points or turnouts, and my main thing here, because this diagram, in this case, I'm working on a track movement in one direction. Obviously, if the trains were moving in both directions, if it was dual direction working, then I would need some extra rules. But as it is, the main thing is that before the point can be moved to the left or to the right, signals 6 and 9 must be at danger. Now, at the moment, I am just doing this as a simple method. In actuality, there is a block here that also should have a rule set up for it, because obviously if there is a train within that block, I do not want the turnout to be able to be moved. So signals 6 and 9 could both be set at danger. Let's imagine the situation where the turnout is going in this direction. So our train has come through signal 10, signal 9. Now signal 6 will already be at danger, at red, because the turnout is in the opposite direction. As the train goes past signal 9 and enters this block, signal 9 will now go to red. So 6 and 9 are both red. Now with the current setup I'm using, I could now move the point 5 while the train is within the block. Now, I've done that for this demo to keep it simple. In the next one, I'm actually going to add in the block occupancy as well. But this is all down to how complicated do you want to make this for yourself. So those first two rules are both to do with the movement of the points. The next thing is signal 9 and signal 6. What has to happen for those to go to clear? Now, if signal 9 wants to go clear, the first thing that must happen is that the point must be in the correct direction. So for signal 9 to be clear, the way I write my system, I have left from the turnout toe and right from the turnout toe. So the way I've got my definitions, for signal 9 to be clear, the point 5 must be turned right. The other thing is signal 6 must be set at danger. Again, if it was trains running in both directions, a signal down here would also have to be at danger as well to stop anything coming in the other direction. But to keep things simple, I'm not going to bother with the blocks and all the rest of it. We're just going to set the point in the right direction, and signal 6 must be at danger. For the point to move in the other direction, which means signal 4 is going to go, signal 6 is going to go to clear. That requires the turnout or point to be, in my case, moved to its left direction, and signal 9 must be at danger. Again, as I've said, for this example, I'm trying to keep the number of rules down, but you can add as many rules in as you wish. Right, moving down then through the setup, I've then left in some functions that list the input types, the inputs, the rules, the monitors, and the dual monitors, just because it just lists it out on the serial monitor, shows me what's going on. I'm then starting the LCD screen. Again, that's optional if you want to have that or not. And then I'm setting up my PCA 9685 boards. I've got both of them. So I'm starting the A up and then setting the frequency, starting the B board up and setting the frequency, and I'm attaching my servo pin. Then from my point of view, I actually go through all the LEDs and I turn them all on, and then I turn them off, and I also move the servo in one direction and then move it in the other direction. That's great on the breadboard because it just shows that everything is working correctly. So as the SketchUp loads, you can see that everything starts up. tests all the LEDs, and then immediately all the signals go to their correct aspects. You'll notice that signals 6 and 9 both go to danger at the start. That's because when you turn the system on, the system doesn't actually know where the point motor is on number 5, point 5, so it sets them both to danger until the first button is pressed, and at that point it starts to work the block signaling correctly. Now, just looking at the serial monitor output, you can see that it puts my sketch name, the time it was created, and all the other bits and pieces. I'm currently starting in training mode. You'll notice I got an error message for 12.3. Now that's because that is an error message 12, which says that signal 3 is being monitored by more than one other signal. So it's only a warning, but that's what that error message is about. Then, as you can see, it's listing the input list. I've then got the items that I've added into the system and their types and various rules and monitor rules. I've got no dual monitor rules in the system. So once we've exited the or got down through all of those tests, one of the things I then do is start up the interlock rules, as you've seen. So what I first do is I set my signals 6 and 9 to danger. Very important. Then all I did was I set all the other signals, these are all the block monitoring signals, to clear. Obviously they will only go to the aspect that they are allowed to go to based on the block occupancy rules, but that's how the system starts up by default. Once the system is all started and my signals have all been given an initial value, and you could just set everything to stop, to danger, and then set things to clear later, but because it's blocks, I just decided I would set them up right at the beginning. So when we go into the main loop, as before, there is the run interlock. Now this basically calls the interlock processing system, and that checks all the signal monitors and all the other things to see if there's anything that the interlock system needs to do. So that must be in. I've then got my timer, current millis, because you need to use millis for timing. Do not use delay outside of this setup or you're going to have some problems. I've then got the function, as in the previous lessons, that calls this function process buttons. Process buttons works through the array of pins that have been created for my blocks and for my buttons, and it checks if the state of any of those items has changed. If they have changed, just as before in the previous sketches, it's going to call a function called block process or button pin process. Now the block process is quite easy depending on the block that has been triggered, and we know the block. So this would be case 0, case 1, case 2, case 3, case 4. The pin numbers don't have to be in numerical order, but you need to make sure that you're working down your array in the correct order, and it's working on the position in the array, not the pin number. So coming down to that processing system, as the different cases are passed, it's either going to, if the block suddenly gets occupied, in which case my pin state is going to be a 1, so greater than 0. At that point it's going to set the signal to danger. If it's greater, if it's smaller than 1, if it's a 0, then the block is clear and it's going to set my signal to clear. And the interlock system will then decide whether that, in this case, is going to be a yellow or a green. So that is going to happen with all of the block pins. They are just changing the signals that are appropriate to those blocks. And then because of the monitoring system, if I change a particular signal and that is being monitored by another signal, that other signal will automatically update its aspects appropriately. Now, let's come down to the buttons. So for the buttons, I've got my 3 buttons. I've got one button that is going to move the turnout to the right, one button that's turning the turnout to the left, and finally I've got one that is setting the mode state. Now, we've covered the mode state before, so I'm not going to bother with that in this tutorial. But what I want you to notice here is that in the previous examples I've given, when you pressed a particular button, one signal or one turnout was moved. You'll notice now we're moving into power box mode. So this is where pressing a single button now sets a string of commands in operation. So it's going to send a command to the system to check the interlocks that signal 6 is set to danger. Then it's going to say make sure signal 9 is set to danger. Then it's going to check for signal 5 to make sure that, if you like, it is going in the right direction, that it can move to the right. And finally, it's going to check the rules for signal 9 to go to clear. So each one of these commands checks a set of rules. Now, for signal 6 to go to danger and signal 9 to go to danger, there are not actually any rules in the system, because I don't need a rule to set a signal to danger. That would be a little bit crazy. Whereas to set the point to a direction to the right, if you remember from my setup, he says scrolling up. So where are we? Setting up my rules for my signal 5 to turnout 5 to go right. Signal 6 has to be at danger. Signal 9 has to be at danger. So as you can see, pressing one button, I can send a string of commands and it will work through those rules, check those interlock rules one at a time. Now again, watching closely, one of the things I like about this system, because I've got everything running quite slowly with all the diagnostics on, when I move the point or the turnout, you can see that this signal goes to green, but if you watch carefully, you'll see both go red and it works through the actual states. If you watch very closely, you can actually see that it goes red, yellow, then green. But obviously it's only on yellow for a very short period of time. Now, one of the other things, I went out to watch some block signals the other day, and I did notice that when a block signal changes, the next signal in the block, there is actually a very slight delay. I reckon it was 0.1, 0.2 of a second. But just like on my breadboard, you get a very similar thing where you actually see the signal work through its different states with a slight time difference from the next block changing. So that is the first screen sort of finished with. The rest of the work is done in custom functions, and there's nothing really new in here. Obviously I've got some bits that deal with the buzzer, and we've got the sort of interlock mode that just writes some information to the screen. But the main function that is of interest is the int update layout. And this is the instructions that you would then send to your electronics that are controlling your signals and turnouts. So in my case, case 1, from my point of view, signal 1, if you like, the item 1 number on my diagram is a signal. So that has a number of states that it can be, and depending on the value that's sent across, I set the states. Now, because it is a 3-aspect signal, case 0 is always danger, so I am setting the red LED on, yellow is off, green is off, and of course if it then goes to 2, yellow comes on, danger is off, and green is off. And if it's case 2, sorry, then it goes to green. As I showed in the previous system about the block signaling, if you've got 4-aspect block signals, then you're going to need a case 3 in here as well. Case 2 is also a signal, case 3, case 4, and then we get to case 5, which is my item ID 5, which is my turnout. So with my turnout, all it's going to do is send an instruction either 90 or 130 degrees, depending whether it is moving to the left or the right. 6, 7, 8 is a virtual signal not being used. 9 and 10, 11 again, another virtual signal not being used. So I've worked through all my different items. That is basically it. There is the other item of the sketch which just deals with sending the information to the LCD screen, but I've dealt with that in a previous video. But that's all that is required to fully automate your signals, and you would just add more and more cases in for each point or turnout or each signal as you add them into the system. So going back to the breadboard, as you can see, we now have a way to automate diverging signals. Again, if blocks ahead are at danger, then you can see that that has an impact in the next signal along. So block signaling over converging tracks, that's how it's done using Interlock++. So that's it for today's video. Please click the like and subscribe if you can, because it really does help the channel and gives me a bit of encouragement in doing more of the videos. I'm now going to get on with the diverging tracks video, so hopefully both the videos will be released at the same time. Thanks again for watching, and I'll see you in the next video. Bye for now.